Hello, everyone. I'd like to welcome you to the November 2024 DAS meeting. So first item on the agenda, do we have any new members like to introduce yourselves? See a couple new faces.
Well, guests.
Or guests. Yes, you could say guests.
Ashley, yeah, it was my second
Hello,
time
Ashley.
here.
Very nice.
Welcome. Here on Thursday last.
Yeah, that's awesome.
Hey, look, Rob.
You guys want to introduce yourself?
Here, Rob and Diane.
Well,
We were here, I guess last week. So welcome back.
Fantastic. All right, welcome. All right, so next item is dues. Can you tell us a little bit about that?
We've begun the collecting dues for 2025, and about over half the club is already renewed. So and it's even getting higher every second.
Half plus one.
It's like 60% of the club is now renewed. So thank you guys for renewing quickly and everything. You know, the dues go a long way to support the club, and it's it's a big help. And if you haven't paid your dues yet, you probably got an email from me yesterday, actually from DOS Mount Cuba, but it was from me, giving you 4 different ways that you could pay your dues. One is by coming to a meeting and giving $30 of some sort to any officer, or you can mail it to me. It's on that email, or there's a couple PayPal links ways of paying it. So we encourage you to continue membership in DOS. Like you say, your dues go a long way to making the program what it is. Thanks.
All right, very nice, thank you. And do note that 60% of the club renewing in just like what, 15, 19 days? That's awesome. Like that's really fast, so incredible. Thank you very much for everything you do, Bob. That's great. All right, next thing, Jeff, you want to tell us about the DAS holiday party?
Yeah, so next month is December, and per usual, we are going to do, in lieu of a traditional meeting, we are going to do our holiday meeting. There will be no board meeting, and there will be no organized meeting in sense of this. In lieu of that, we will have something a little bit more casual starting at 7 p.m. We'll just have a very casual holiday get-together. The 2 main features of the get-together is, number one, we always do a potluck. So please feel free to bring some food or drink, sweet or savory, to share with your fellow club members. There are outlets scattered around the library, so if you need a crock pot or something, we should be able to accommodate plugging that in. And then the other aspect, as we often or always do, is to organize a swap meet. The club will have a number of folding tables set up around the lobby. And if you have any old gear or I guess not so much old, but unwanted gear, bring it out, set it up. We'll give you the table. You take it from there to give you an opportunity to sell, trade, barter, donate, whatever you want, any equipment that's taken up room that you'd like to get rid of. In addition to that, the club has recently been donated 4 telescopes by Elizabethtown University, and those 4 telescopes are going to be offered up via a in-person silent auction. And basically there'll be an envelope, you'll write a bid, stick it in the envelope, whoever offers the most money will get it. Again, the caveats, it will be in person. I know we've done some email-based silent auctions in the past. This will be in person. Details about what the scopes are with maybe, I guess, some photos and some vague descriptions will probably be in the focus, but also in an email to the groups.io. The caveats are come prepared to pay for it and come prepared to take it home that day. So an extra enticement for folks to come out. It's 3 roughly 8-inch SCTs.
Yeah.
So that's, but more details to come on that.
And 1 reflector.
Yeah. If anyone has not attended one of our holiday parties before, at the end of the meeting during the social hour, just chat with any of the other members just to get a sense of, filling in any gaps that I might have left in. But it's a good time, a lot of fun. Hope to see you all there.
Very good. And I also want to emphasize that it's a great opportunity to get some awesome, oh, welcome. Nice to see you.
Got a little lost.
Very glad to see you.
And I had trouble getting it from.
No problem, no
Oh.
problem. Oh, very good. That's our speaker for a few minutes. It'd be lovely. So as I was saying, the holiday party is a great opportunity to get some nice snacks, to have some nice camaraderie, and maybe get some great astronomy deals for Christmas. That'd be great. All right. Next item on the list, calendars. Lynn?
Two people, Rod, is Rod gonna be
Yes.
doing? I have your calendar. You ready for the Eric circle? Okay.
Yeah, I don't think so. What? And then next thing is the AP SIG.
Yes, the next meeting of the APC will be Saturday, December 7th. Don't know what time yet. Depends on who steps forward to offer a site for a meeting. And details will go out over groups.io 2 or 3 days ahead of the meeting.
Very good, thank you. And then the next item is the book club. Mary, got any details?
Good evening, everyone. I'm just coming to you via audio. The book club will meet this Thursday, November 21st at 7 p.m. via Zoom. And we will be celebrating the 125th anniversary of the American Astronomical Society. To honor the occasion, we're going to discuss a series of papers that are posted to the AAS history website. I wasn't able to directly share them with you because of copyright considerations. We will be discussing those. We're honored that Dr. David Dvorkin, an emeritus senior curator, history of astronomy and space sciences at the Smithsonian National Air and Space Museum, will join us to discuss the early history of the AAS. And remarkably, Kevin B. Marvel, PhD, Dr. Marvel, the executive officer of the American Astronomical Society, who's been in that position for decades, is also going to join us. And he'll be picking up the history of the AAS after Dr. Dvorkin stops his presentation. It should be a really remarkable meeting. I encourage you to attend. And if I may just take another minute, because we're not having a December general meeting, I'd like to hawk our December meeting of the book club on December the 19th, also via Zoom. We'll be discussing What an Owl Knows, the new science of the world's most enigmatic birds by Jennifer Ackerman, who the book has been receiving incredible reviews. We will be jointly presenting with Ian Stewart, an ornithologist with the Delaware Nature Society. And thanks to the generosity of Diana Metzger, Carla Blom, the executive director of the International Owl Center, will be joining us to discuss the Ackerman book and the work that she did at the International Owl Center. Diana Metzger will be discussing her many trips to the Owl Center, and the meeting will be led by Sheila Vincent. Thank you very much.
Thank you very much. All right, any other announcements that I missed? I think I got everything on my list. Okay, good. And then Jeff, without further ado.
Yeah.
You can introduce
So
yourself.
our main meeting talk for tonight, we are rejoined by Professor Paul Halpern. I keep repeating that I don't mess this up. I was about to say he is a professor at the University of the Sciences, but that's old news. He is a professor at St. Joe's University, which I understand kind of.
It's assumed. It was like an accretion process.
There we go. So Paul has written a number of books, and he's come and given us talks on a number of them. The theme so far had been he's always written books about pairs of famous scientists. And he's bucking the trend because his latest book, which came out, within the past 6 months or so, or?
January.
Yeah, January, is all about the allure of the multiverse.
Yes.
So let's all welcome back Professor Paul Halpern. Oh, sorry, one more caveat.
You have that on your computer, right?
Yes.
Okay.
Yep, we're good to go. One click away. Paul has brought a couple of copies of the book and he will be offering them for sale at the end of the meeting. The club is going to purchase a copy for the club to go into our library, but if anybody would like their own personal copy, Paul would be happy to pry some of the money out of your wallet.
Yeah, $30
$30
per signed copy.
There we go.
Yeah.
Paul, all yours.
And where should I stand there?
Wherever you would like.
Okay.
Oh, boy, is that it? I can't.
Yes, that's it.
To the left, tell me when. There he is.
You need to share the screen, Doug.
Thank you.
Very important.
And again, I still can't see, so someone can guide me
Right.
right here.
To the left, there. Yeah, and then share. And then you want to. Yeah.
Oops.
Move it all the way to the left. All the way
I want to peg this one
Yeah, please.
and then do this
Yep.
and then do this. And now I think we're all set, right?
Yep, okay.
Paul, one quick logistical question. Do you prefer questions as they come? Or do you prefer people to hold off till the end?
As long as there are occasional questions, but if there are too many that
Then you'll-
interrupt my flow, then go back to.
And that goes for folks here as well as the folks online. So,
Okay,
Paul,
Thank
all
you.
yours.
thank you. So hello to everybody here in person. Hello to to the Zoom audience. Thank you to the DS and Jeff for inviting me back here. The last time I was here, I think I was one of the first in-person speakers. Like
Yep.
it was kind of historic.
Yeah.
It marked the return of normalcy, I think.
Yeah.
Except that it was me, so it wasn't quite normal. So anyway, so today I'm going to be talking about a little bit about the multiverse, and one of the first reactions from hard-headed astronomers, scientists, and so forth is like, hey, wait a minute. If that's not observable, then why even talk about it?
Is it not advancing?
Yeah, here we go.
No, you should be good.
So that's why I say beyond the limits of direct observation. So I want to make the case that sometimes it's important or interesting to talk about things that are beyond direct observation. So the scientific method, very famously, involves testing, retesting, verifying, seeing if something is falsifiable. That is, can you find a contradiction to it, or can you affirm it through direct testing? And a good example of that is back in the 1920s, this famous physicist Paul Dirac came up with an equation. He solved it. He said the solution was an electron, but there's a positive solution here, so there must be a positive electron. He thought it was a proton at first, but then it was the same mass as an electron. So he finally concluded there must be a new particle called a positron. 4 years later, Carl Anderson looked at cosmic rays and found a positron in cosmic rays, splendidly proving something that was only discovered theoretically 4 years earlier. It's kind of an amazing situation. You go from theory to experiment, and today we know that electrons come in pairs with positrons, and that in the beginning of the universe, there's probably an equal number of electrons and positrons. So that was pretty exciting. In astronomy, of course, direct observation is key. And if you want to either advance science or sell calendars, you have really nice images from space telescopes, like the James Webb Space Telescope has produced brilliant images, and really questioned our theory about galaxy formation and the development of galaxies in the early universe. So also direct observation. But we have limits. So even though the universe is vast, the observable universe is 46 billion light years in radius. Now, if the observable universe is 13.8 billion years old, you might wonder why 46 billion. And that's because the galaxies are moving away from each other and accelerating as they're moving away from each other. So I like to say it's kind of like if you were standing and someone was standing a certain number of feet away and tossing a football at you, you could kind of guess by the speed of their throw and how long it took for them to throw it, how far away they are. But if they threw the football and ran really fast backward, then you would have to take into account the fact that they were running away from you. So their distance from you would be much further away. And that's why the farthest objects in the universe that are within observation are 46 billion light years away from us, because they sent us a light like curling a football and then sort of ran away from us because of the expansion of the universe. So they're much farther out than they were when they sent the light to us. Now, if you look at Einstein's famous general theory of relativity, which describes gravitation, that makes predictions for the whole universe. So it doesn't say the observable universe is one way and the rest of the universe is another way. So you get to the point where you say, hey, wait a minute, can we talk about things that are beyond the observable universe? Does it make sense? So for example, in general relativity, Einstein talks about different possible shapes of space, meaning three-dimensional shapes. So kind of extensions of balloons, but curled along the third dimension. So if you kind of imagine, instead of a two-dimensional surface, you have a three-dimensional surface, and that could be curved in different ways. It could be kind of like an extension of a sphere, kind of like a Pringles potato chip, or like a flat pancake going all the way out infinitely. So if the universe is flat, as most people believe, do we say, well, the observable universe is flat and who knows about everything else? Or do we just say the universe is flat? Well, most physicists would say the universe is flat and kind of assume that things pretty much continue beyond the observable universe, at least for a while, pretty much the same way. So we're talking about things that are not only not observed, but it's never possible for us to observe these things as far as we know, because they're beyond the limits from which light signals can reach us. So if it's beyond where a light signal ever could have reached us, it's forever unobservable, but we can still talk about it. Now, if you talk about black holes and look at images of black holes, you have this dark spot in the middle, and we kind of say, well, that's within the event horizon of the black hole, and that's a region within no light signals can be sent out. Now, radiation very slowly decays from a black hole, as Stephen Hawking showed. It's called Hawking radiation, but we can't really get a signal from an astronaut falling into a black hole. It would be impossible. So therefore, it's something we can't really observe and live to talk about it. But we still talk about what's inside the black hole. We don't say that's a taboo subject. We're not going to talk about it because it's unobservable. So there are a lot of cases, what I'm trying to say is where things are not directly observable, but we kind of infer what their properties are based on other things. Now, anything that's completely unknown invites Hollywood to speculate about it. So I'm old enough to remember the going to the movies and seeing the Walt Disney Black Hole movie, which I don't recommend. So it's probably on YouTube or something like that, but it's just really bad. And the acting is really hammy. It's Ernest Borgnine and was it Maximilian Schell at their hammiest acting. And one of the scenes involves kind of standing on a mountain in the middle of the black hole. You can see on the lower right, and being judged. It's just almost like biblical, but has nothing to do with black holes. So but still, my point is that movie came out around 1979. Black holes were proposed about. The name black hole was from about 10 years earlier. And scientists still consider black holes seriously. So even though there's a lot that's unknown about black holes, and there are strange movies about black holes, scientists say, hey, wait a minute. There are real black holes. We're going to talk about them no matter what. No matter what Hollywood says, we're going to talk about the real black holes. Now, let's look at the multiverse, however. There's a lot of films about the multiverse, which are range from entertaining to silly. And they do not in any way depict what scientists are saying about the multiverse. What scientists are saying about the multiverse is perhaps in certain models, there are domains, either on a small scale or on a very large scale, that are unobservable. So regions that are unobservable. But anyway, some of the multiverse movies that came out in recent years are Doctor Strange in the Multiverse of Madness, the multiple Oscar-winning Everything Everywhere All at Once, and the Spider-Verse movies. And of those, probably my favorite are the Spider-Verse movies. So they're very well done and good character development. Everything Everywhere All at Once is a little bit intense. It was interesting, but it was just parts of it. I was very hard to follow. So, but anyway, it won the Oscar and it had good acting. So when we talk about the multiverse, we can talk about the cultural multiverse versus the scientific multiverse, and they're very different, as I'll show. But the cultural multiverse is what appeals to the public. So, for example, one reason it appeals is the idea of seeing beyond the frontiers of observability. So, what's beyond, just like we say, what's beyond the interior of a black hole? What's beyond the limits of space and time? What's beyond the limits of what we know, our lifetimes and so forth? What if we can see alternate lifetimes? And that brings in the question of what if. So a lot of times we make choices in our lives. We get a job offer in Wilmington, and then get another job offer in New York, and we, balance the two and say, well, Wilmington is not as expensive as New York, and we decide to go there. But then we don't know if we had chosen the job in New York, maybe it would have been pricier to live there, but maybe there would be other opportunities there. So we wouldn't know. So there's the things we wonder about. We never know who we would have met, partners, friends, and so forth, if we made different decisions about where we live in our lives. So that's fascinating stuff, and there's a lot of movies about that. So, for example, every time we catch a train, so if you go down to Wilmington and you try to catch the Amtrak train, if you just make it, if it's just about to pull out and you jump on, you're the last one to jump on, and then it pulls out, then you might say, wow, I'm really, really lucky. But if there was an accident with that train, you'd be like, oh, why didn't I just wait for the next train? Or you just don't know if you had waited for the next train, maybe, you would have met someone who would be really important to your life. So you really don't know if making the train or missing the train is better for you. So these are fascinating questions. Now, one of my favorite multiverse movies, and by the way, if you're interested in my picks for top 10 multiverse movies, just Google my name, and not right now, but Google my name and top 10 multiverse movies. And I have a list that came out earlier this year associated with the magazine New Scientist. And Sliding Doors is one of them. And it's really interesting because a woman, one version of her just misses a subway train, and the other version just makes a subway train. And then the filmmaker continues the two branches to see what happens to her if she just makes the subway train, just misses it. She just makes the subway train. She comes back to her apartment where her boyfriend's there, and he's having an affair, and she finds out about the affair, breaks up with him, meets Mr. Right, and changes her life, gets a better job, and so forth. If not to give too much away, but then if I should say spoiler alert, I'm not giving away the ending now. And if she misses the train, then she doesn't realize until later that her boyfriend's been cheating on her, and she stays with him, and she stays with her job, but then I'll just say there's a twist at the end, which I won't tell you about. But now let's turn to science, which is what we're really interested in. So, the general public can watch these films about life, but we're all interested in science. So does it even make sense to think about things that are not directly observable in science? And the answer is yes, in some cases. There are theories that predict multiple universes that I think are worthy theories. Now, the story of the scientific multiverse goes as far back as one of Albert Einstein's last talks in 1954 at Princeton University. The last talk I gave on this topic was actually to, I don't know if you know, there's a Princeton Amateur Astronomical Society there, and they invited me last month to speak up there. And it's kind of cool whenever I'm in Princeton, I'm like, yeah, just like a few blocks away from here, Albert said this, and then the rest was history. So that was fun. But anyway, so up in Princeton, Einstein gave a talk, and the topic was about some of the problems with quantum physics. And it was to John Wheeler, who's the one who coined the term black holes, relativity class.
I'd like to quote the composer's notes about the piece.
And Einstein had a lot of beefs with standard quantum physics. And one of them has to do with quantum measurement theory. So in orthodox quantum mechanics, which is the quantum mechanics of people like Niels Bohr and John von Neumann, what happens when you take a measurement is that the quantum state splits into something like a drawer with a lot of dividers. So imagine you have a drawer, and the drawers, let's say, used for change, and you have all these dividers, and one of them has nickels, and one has pennies, and one has dimes, and you put different things in different dividers. And then once you make a measurement, this state collapses into one of those possibilities. So if you were measuring position, the drawer divides into dividers based upon all the different position possibilities. Then you finish the measurement, it collapses with a certain likelihood into one of those possibilities. So for example, electron could be 1 nanometer to the left of a marker, 1 nanometer to the right of a marker, or just on the marker. So let's say you take a measurement and it ends up being 1 nanometer to the left of the marker. That would be your result. And that depends upon you taking a measurement and this idea of collapse. So here's what it looks like before collapse and after collapse, taking the measurement. Now, this is called Hilbert space, this set of all possibilities. And there's a lot of strange things about Hilbert space. First of all, depending upon which measurement you take, the dividers can go different ways. If you measure the position of an electron, it will divide into position dividers. If you measure the velocity of an electron, then suddenly you get a different set of dividers, all the possible speeds. But you can't measure them both at once. That's because of Heisenberg's uncertainty principle. So you have to decide. And once you decide, the dividers just magically appear and divide up the state into those possibilities, and it collapses into one of those possibilities. So that's strange. Hilbert space is an infinite number of dimensions, which reminds us of a story called Hilbert's Hotel that supposedly Hilbert told about a hotel with an unlimited number of rooms, and it has a no vacancy sign. So all the rooms are occupied. But then you drive up and you say, you know, I really need a room. And the innkeeper says, no problem. And then gets on a loudspeaker and says, hey, you in room 1, move to room 2. Hey, you in room 2, move to room 3. And has everybody move one room down, and then there's a vacancy for that person. But then another person comes in who happens to be a general and says, I have an army, it's infinite number of people, and we all need rooms. And the innkeeper says, no problem. Everybody needs to move into an even room. So the person in room 1 needs to move to room 2. Person in room 2 needs to move to room 4. The person in room 3 move to room 6, and so forth. Double your room number. And then all the odd rooms would be open, and then there'd be an infinite number of rooms for that harmony. Well, that's the way Hilbert space is for quantum states. It has an unlimited number of dimensions. So quantum physics, even if you don't talk about the multiverse, is very, very weird. It has space with infinite number of dimensions. So that's why if someone says, quantum physics is great, but I don't want to talk about the multiverse, I think, hey, wait a minute. They're both kind of strange things. So you have to pick your strangeness. Now, Einstein was baffled by the idea that human choice for measurement could do this divide and create this collapse. He thought that nature must be independent of people because, of course, nature has been around for billions of years. What about before human beings? And he asked at the talk whether a mouse could trigger quantum measurements. And in the talk was a young student named Hugh Everett III, who was from Washington, D.C. And he was a very inquisitive young man. And he said, you know, old Albert's right. You really should have a quantum theory that does not involve human beings. In fact, human beings are made of atoms, so they're made of quantum states too. So we really should have a theory that includes both atoms and human beings as part of the same thing. And in fact, the whole universe should be part of the same thing. So you start talking about a universal quantum state that includes everything in the universe. So he started developing a PhD thesis under the supervision of John Wheeler, the one who invited Einstein there. And Wheeler was very open to a lot of strange ideas. And Everett said, okay, let's discard the idea of quantum collapse and see what happens. So no one's going to trigger a quantum state to collapse down into one possibility. In fact, all those possibilities are always going to exist. So if an electron was originally a mixture of 1 nanometers to the left, 1 nanometers to the right, and then at the center of some marker, then it will maintain those positions. But what will happen is the human observer, will split like these triplets here, split into 3 identical possibilities, each of whom will think that they're the right one and have the right answer. So one observer will say it's 1 nanometer to the left, one will say it's right in the middle, and one will say it's 1 nanometer to the right. So therefore, they'll all disagree, but the thing about the split is it happens seamlessly. So there's no indication that something has happened. So if you're splitting or I'm splitting, you don't feel the split. It just happens. And you go through life either thinking that an electron was here or here or here. It's not very dramatic. So if you wanted to make a movie about a quantum multiverse and you have a scientist instead said like, I could have sworn the electron was right over here, not right over here, it wouldn't make a very exciting movie. But that's the way it is in Everett's theory, which later became called the many worlds theory. And Wheeler was open to all sorts of strange ideas, such as an earlier idea by Richard Feynman called Some of Our Histories, that when electrons interact, they interact in many different ways simultaneously. Now, this happens not in different parallel universes, but different strands of our universe, and we don't actually see the possibilities. So it's not that human beings split, it's just that the electrons do a bunch of things at once, and then you get a result. So that's the difference between the two ideas. And this idea that some of our histories that electrons interact different ways simultaneously is very widely accepted. And these bifurcation ideas are talked about a lot in literature. Some of you might be familiar with the Argentine writer Jorge Luis Borges, who wrote a story called The Garden of Forking Paths, imagining what would happen if in different parallel realities you have different relationships between people. that two people can be friends in one reality and enemies in the other reality. So it's a very intriguing short story. Now, unlike Feynman's Some of Our Histories, in the Everett hypothesis, reality actually splits. So you have different universes with different near identical copies of observers. So near replicas of people. And there's a famous thought experiment called the Schrodinger's cat experiment, where a cat, and this is not really done, so don't worry about the ethics of it. But in the thought experiment, a cat is placed in a box with a vial of poison and a radioactive sample and a Geiger counter. And if the radioactive sample decays, then it triggers the Geiger counter to break open the flask of poison and to kill the cat. But if it doesn't decay, then the cat is spared. And according to the idea of quantum superposition, until you open up the box, the cat is in a mixture of alive and dead, and is a kind of zombie-like state of living and dead. Now, no one really believes this, but it was a hypothetical situation proposed by Schrodinger to try to illustrate some of the absurdities of quantum physics. Well, in the Everett version, the cat is still both alive and dead, but in parallel universes. So in one version, the experimenter will open up the box and see a dead cat and be very upset, and the other, they'll open up the box, see a living cat, and rejoice by the result. So you have these two strands. So the cat is in a mixed state, but everything's in a mixed state, so there's no real contradiction there. So soon after Everett proposed his thesis, Niels Bohr, who was supporting the orthodox point of view of quantum physics, visited Princeton, and you could see Bohr right here in the middle, and this is Everett here. And Everett was, I guess, upfront enough to be able to talk directly to Bohr and say, "Hey, I have a better idea than you do." So, especially after, he and his friends used to have these sherry parties in the dorm rooms. They drink a little bit of sherry, which would fortify them, and then they'd be willing to confront their elders and tell them they're wrong and so forth. So, according to the stories. But Bohr was very famous at the time. He was practically royalty in Denmark. When Queen Elizabeth II visited visited Denmark, she paid a call on Bohr's mansion. He was that famous. So he wasn't willing to really change any of his ideas because he thought, well, they've all gotten me so far. What if I'm overthrown and then I'm no longer a famous person in Denmark? That would be bad. So he wouldn't even listen to any young upstarts. But what happened is Wheeler, as Everett's advisor, kept pushing this and sent a physicist, Bryce DeWitt, who's pictured here, a paper by Everett. And DeWitt was another hard-headed physicist and at first said, "Hey, wait a minute, I don't really feel any splitting. This is ridiculous. This paper is nonsense." And then wrote back to Wheeler, and Wheeler passed along the idea to Everett, and Everett wrote back and said, "Hey, wait a minute, we think that Copernicus was right about the Earth turning around, Earth spinning. Do we feel the Earth turning?" And DeWitt wrote back and said, "Touche, young man, you have me there. So maybe you're right that the world is splitting." And then became the biggest advocate of Everett's ideas in the world. And in around 1970, published a Physics Today popular paper and a scholarly paper. And he's the one who came up with the name, the Many Worlds Interpretation of Quantum Mechanics, a catchy name, which caught on and made the idea much more famous. Meanwhile, Everett was very discouraged because between 1957 and 1970, no one talked about his idea in physics, or ignored it and so forth. So he went into the defense industry and forgot about his idea. But then there was a revival once DeWitt started promoting it. By the 1980s, the idea underwent a revival, and Everett was invited to speak at the University of Texas and was kind of given a little bit of celebrity status for coming up with the idea. So he was very happy. Unfortunately, Everett died at a pretty young age of a heart attack. I think he was only in his 50s. And his son was there at the time, sadly enough. But his son is now a rock musician. His name is Mark Everett, and he's the lead singer and songwriter of a rock band called the Eels, and has written stuff about his father. Well, to continue with the story, around 1970, a physicist named Brandon Carter, who's originally from Australia, but he was working at Cambridge at the time, said, this Everett idea, this is really interesting, the idea of parallel universes. Maybe we could use this to devise a litmus test for why things are the way they are in this universe. Maybe we can imagine the universe being a set of possibilities, and in some of them, things are less hospitable than in this universe. And the reason he said that is because there are a lot of things in this universe that seem like too good to be coincidences. Like, for example, the charge of a proton and the charge of an electron are exact opposites to each other. So you have neutral atoms. If the charge of an electron was slightly less than the charge of a proton, then all material will be positively charged and we repel each other, and you wouldn't be able to have living beings and planets and things like that. So we need electric neutrality. Gravity is strong enough to create planets and the solar system and so forth by taking a gas cloud and coagulating it and creating something like the solar system. But it's not so strong that the universe collapsed right after the Big Bang, because if gravity was a lot stronger, the universe would expand and then almost immediately collapse, and then we wouldn't be here. So Brandon Carter asked the question, why is our part of the universe or our universe itself special? Let's look at all the ways. And this was in opposition to what was more widely accepted at the time, the Copernican principle that says, or sometimes called the principle of mediocrity, that says that we must be in an average place in the whole universe. And Brandon Carter said, wait a minute, we can't be exactly an average place, because if we were in the center of the galaxy, we'd be irradiated, and the stars would be too large to support planets like Earth and so forth. So we must be in a certain part of the galaxy, and then also in what's called the Goldilocks zone of the solar system, not too hot and not too cold. So he put all these things together and said, maybe we're in a special part of the universe, or maybe our whole universe is special in a set of a multiverse, the set of all universes, because it's the only one that can support life. So if you might have other universes where gravity's stronger, gravity's weaker, electricity's stronger, but those will not enable planets with life ultimately. They might collapse, they might expand too quickly. So we're just the right type of universe in the set of all possibilities. So that's called the anthropic principle. So one thing that's really special about our universe that we can be very thankful for is the creation of carbon. So if you look at the nuclear ladder, how elements are built up in the cores of stars. So elements, the early elements like helium are built up in the Big Bang, but then if you want to create carbon, you need the coincidence of basically 3 helium atoms coming together almost simultaneously, with maybe a trillionth of a second in between them coming together. So 2 come together, and then a third one comes together with the 2. because if two helium atoms get together, it forms an element called beryllium, which is highly unstable. And under most circumstances, it would just decay back down to a lighter element. So then a third helium atom comes along, it would not be able to bond with the beryllium and become carbon. So carbon is the equivalent to 3 helium nuclei. So you need a 3 helium nuclei to kind of come together almost at once. And there are quantum rules that allow that to happen, that if 3 helium nuclei come together, it forms a stable form of carbon called carbon-12. And it can happen in temperatures above something like 100 million degrees. So it can happen in stars with cores that are starting to collapse. So old stars where the cores start to collapse are places where carbon can be formed. And then from carbon, you can build up a lot of higher elements and all the way up to iron. And then beyond iron, the higher elements than that are created in supernova explosions. So you can basically explain all the elements in the universe. But if you didn't have this coincidence where you have 3 helium atoms coming together and there's this quantum transition into carbon, because they have similar energy levels, then you would have a bottleneck and you wouldn't have been able to build up the higher elements. So you might imagine other universes with slightly different quantum rules where you would have the bottleneck and those universes would never create carbon and you probably wouldn't have any life in those universes, unless you believe that you can have life without carbon. So the next step in the history of the multiverse is the idea of inflation, cosmic inflation. Now, cosmic inflation was proposed in the late 1970s during a time, some of you may remember, when there was a lot of inflation in the economy. And Alan Guth came along and said, why is the universe so smooth? Why is it so regular? And he said, let's look in one sky direction and count the number of galaxies. Look in another sky direction, count the number of galaxies. Look in one sky direction and look at the average temperature of the radiation in that region. Do another part of the sky, look at the average temperature of radiation. And you find there's remarkable smoothness. So he said, you know, if we reverse the Big Bang just the way it is, back in time, you still reach a point where when the radiation was released and matter was created, the universe was still pretty big. So you would just have this cloud, and that cloud, you would have to explain why that cloud was so uniform some 300,000 years after the Big Bang, which is when atoms and radiation was created. So that doesn't really make sense. You can't really explain why the universe is uniform with the standard Big Bang theory, but the inflationary model says when the universe was first born, within a trillionth of a second, there was some energy field, some energy event that triggered an ultra rapid expansion, taking things that are subatomic size all the way up to the size of about a baseball. So a part of the universe that was smaller than a proton suddenly blew up within a trillionth of a second to something that's size of the baseball. And then that baseball size part of the universe expanded much more slowly and expanded for 13.8 billion years and became the observable universe that we see today after 13.8 billion years. But you needed this rapid burst. And the reason you needed the rapid burst is because that smoothed everything out. It's kind of like taking a wrinkled sheet and having people on all sides of it and stretching it simultaneously, and it creates a smooth sheet, flat sheet. Well, that's the way the universe is. It's regular, it's flat, and so forth. And as a bonus, inflation blows up tiny little glitches, tiny little irregularities to something that's just the right size to form the seeds of structure. Meaning you have irregularities in the universe that create little lumps of material coming together. And then over millions or billions of years, those lumps of material build up and cluster together and form structures like stars and so forth. If you didn't have those tiny irregularities, then the universe would be completely smooth, absolutely smooth, and then you wouldn't have stars and galaxies. So inflation seems to do the trick of smoothing things out on the large scale, but then allowing for structures on a smaller scale. So it's a really amazing theory with a lot of predictions, but it does go on.
FMT radio network.
Is there a question online?
Okay, a voice from another universe, yes.
It's one from this universe.
Okay.
Where does gravity come into play in the expansion theory of the universe?
So, so the expansion is expansion of space itself.
Yeah.
And that's just a result of Einstein's theory of relativity. And if you have certain types of energy in the universe, they can cause things to coalesce, matter and energy. They can bring things together, or they can push things apart. And that's just an effect of Einstein's theory. It says that different types of energy and matter have they warp space. They can make space bigger, they can make space smaller. It depends on, what you add in that region. It's kind of like a garden. And if you add topsoil, fertilizer and stuff, you'll grow things. But if you add the wrong stuff, like you accidentally, take out a jar of something that's like lethal to plants, and you put it in that garden, like everything's gonna wilt. The same with the universe, depending on what you put in different spots. You can have ultra rapid growth, slow growth, and collapse.
Businesses. More information is at capegazette.com.
Rob, can you? I'm sure I'll mess that up.
Okay.
Sorry.
Universe.
So then essentially the seeds of material create their own tiny space-time warps.
That's right, yeah.
Okay.
And the
Everybody
larger
else is muted.
things, like the sun, creates a little dent in space-time.
Mhm, mhm.
Yeah.
All right, everybody's muted.
Okay.
Yeah.
But if you have the right type of energy field, you get rapid expansion. And Andre Linde and others showed that if it happens one place, it can happen a lot of places. So if you have ultra rapid expansion in this part of the universe, you have all these other bubbles. And that's called the bubble universe, also known as eternal inflation. And most people who support inflationary universe theory, think it's happens a lot of places, not just once. So that also implies a multiverse, because if our universe blew up, there's probably other universes that are beyond observability that blew up in other parts of the original space. So that's another way of describing the multiverse, called the bubble universe model. Yeah. So this is actually a type of multiverse that's possibly testable. We can't really take a spaceship and go to another bubble universe, because it will be well beyond observability today. But it's possible that our universe and another bubble universe collided early on in their history when they were very close together. And there's a theory that the collision would have created a scar in the cosmic microwave background, which would be the hot radiation of the early universe that's cooled down today, and is the background hiss we can detect with radio telescopes. So people have been trying to use radio telescopes and other ways of measuring the cosmic microwave background to try to find these scars. And two of the probes from recent decades are the WMAP probe and the Planck satellite, and they were looking for, one of the things they were looking for was scars of collisions between universes. And this professor, Hiranya Pires, has been very active in looking for bullseye signals, which she and her colleagues predicted would be the result of cosmic collisions with other bubble universes. And so far, I interviewed her for my book, and she said, very honestly, she said, so far we haven't really found anything significant, which I appreciate in this age when some scientists, greatly exaggerate their data, and she really underplayed it. She said, it's worth looking, because if you do find a signal that you can verify, then it would be revolutionary. So we should keep looking for them. There's another place where multiverse theory emerges, and it's something called string theory, which is the idea that the universe, instead of having point particles, is full of vibrating strands of energy. And it's a little bit like musical chords. And depending upon how these strands vibrate, it creates different particles in the universe. So one type of vibration creates an electron, another type might create quarks and photons and so forth. That's string theory. It's a little bit controversial because it hasn't been proven experimentally yet, and it's
an episode on Star Trek that
yes. Well, once again, there's the cultural aspects of science, and then there's real science. But anyway, some people are ardent believers in string theory, and some think it's not really science. So another controversial area. But string theory predicts that you need at least 10 dimensions or 11 dimensions of the universe. So, well, we can only see 3 spatial dimensions. So this room has 3 spatial dimensions. And then we have the dimension of time, so that's 4. So then the question is, if string theory is only mathematically viable in 10 or 11 dimensions, what happens to the other 6 or 7 higher dimensions? And the idea is that they're twisted in pretzel-like shapes, so tiny that you can't observe them. So they're dimensions that are so tiny. It's a little bit like if you took a piece of dry spaghetti and you held it up, not vertically, but face on, you would see a tiny little dimension, which is the end of it. But if you looked at spaghetti from a great distance, it would just look like a straight line. It would look 2-dimensional. It wouldn't look 3-dimensional. Or 1-dimensional even. So the thing is, you can have higher dimensions that are undetectable because they're curled up. But the problem is, according to Eugene Calabi and Yao, I forget his first name, that there are 10 to the 500 possibilities of ways to take the universe and put it into a pretzel.
Question. What do you think about hypercubes then? What's your opinion on that?
Well, that would be the simplest extra dimension. So that would that's relatively easy to visualize. Much easier to visualize than to imagine like 10 dimensions or something like that. But hypercubes are pretty cool. So anyway, so there's 10, but the problem is there's 10 to the 500, which is 10 followed by 500 zeros, ways to twist up these extra spaces. And each one gives you a different dynamics of the universe. So the question is, which one is right? So some people say there's a landscape of possibilities, and that most of them, if not all of them, produce nonsense universes that don't work. And then only one or a handful produce universes that do work. And maybe if we're lucky, we can sift through all those possibilities and show why our universe is here and why it has to be here based upon all the other possibilities that don't give you life. So it's a bit of a stretch. Now, another use of the multiverse is explaining why a term called the cosmological constant is small but not zero. And the theory of the cosmological constant started in 1917 when Einstein couldn't quite get a stable universe. He kept getting a universe that was expanding, and he thought that was a mistake. So he added a stabilizing term, which is a cosmological constant, which was a little bit like a fudge factor he put in just to make his universe stable. And it counteracted gravity. But then later, when Hubble discovered the expansion of the universe, Einstein dropped the term and said it was his greatest blunder. He should never have added the term, because if he didn't add the term, he would have predicted an expanding universe, which would have been a great prediction. But then in 1998, they discovered that the universe is not only accelerating, but not only expanding, but accelerating its expansion. And adding in the cosmological constant gives an extra boost to the universe, which could explain the cosmic acceleration. But it has to be a really tiny cosmological constant, just the tiniest extra boost that causes the universe to speed up. So here's the different possibilities for the universe. One is big crunch, which is collapse. And then this red one is accelerated expansion, which is what we believe to be true today. Now, quantum theory, because of the energy in space, predicts a cosmological constant. You can actually calculate it, but it predicts a huge one, much, much greater than the one in astronomy. So that's a crisis in physics, to say, why do we get a tiny cosmological constant when quantum theory predicts a big one? And once again, the multiverse comes to the rescue, because you can imagine an array of myriad universes, each with different cosmological constants. And most of them would be really large. But then you have this outlier universe where the cosmological constant, just by pure chance, is really tiny. And that lets the universe expand at a normal rate rather than blowing up. And that becomes our universe. So we're kind of an outlier. So that's another theory about the multiverse. So here's the Weinberg multiverse. And Weinberg was a Nobel Prize winner, so this was taken pretty seriously. So our universe is then an unlikely universe, but it expands slowly enough to allow for gravitational clumping, leading to stars, galaxies, planets, and life as we know it. So, I'm going to end here in conclusion. Multiverses in fiction and science are very different. There are many types of scientific multiverses, going back to the many worlds theory, the anthropic principle, eternal inflation, string theory, and the idea of a landscape with different cosmological constants. And for more about the multiverse, I cover a lot of other topics, plus the history and the personalities in my book, which I have copies here, and I'd be glad to sign after questions and answers, sign copies, personally autographed for $30, which is the list price of the book. So I'm going to stop here and see if there are any questions.
So in the beginning, and I know it was an analogy, but you drew the parallel with like black holes in terms of setting up this motivation that we can think about things, perform thought experiments, even do some theoretical science on something that we can't extract data from.
Right.
But, and I'm not versed enough in like the entire history of black hole theory, but data cannot escape a black hole, but we have evidence of their existence.
From the outside, yeah.
Right. This is different, right? Or maybe help me make that leap. What actual observable evidence do we have that might suggest?
Well, someone who's a believer in inflation and says inflation is right for 10 reasons. You know, it explains the flatness of the universe. It explains the temperature distribution of the universe. It explains structure formation. It explains galaxy distribution in the universe. So there's so many reasons to believe in inflation. And we have a model for inflation, and this model says that there must be multiple universes.
The
So
only,
it'll be indirect
the only
evidence.
viable explanation
Right,
currently. Okay.
Right. So that's what, for example, Andre Linde of Stanford would say.
Yeah, but is that something that just fits a mathematical equation? Or,
Yeah, if it's general relativity and quantum field theory of energy fields. If you combine the theory of energy fields and Einstein's general relativity, you get the prediction of blown up expansion.
But is that, is that a situation where there's a possibility? It's possible, but it doesn't necessarily mean you have to have it.
Well, I've asked people who are, you know more than I do, people in the field of cosmology who are active researchers, and say, can you tweak this model so you just get inflation in one universe? They said, well, you can tweak it, but it's really hard to do. It's much easier to say you have multiple universes. So
Actually, on that note, a couple of things, and we might be diving a little further away from physics and a little more towards philosophy. But in the pantheon of science, right? Is it of more import to have mathematical convergence or observational convergence? What I mean by that is, and I'm truncating a lot here, so feel free to nitpick, but my understanding as it comes to a lot of the multiverse theories, not all of them, but most, is that they are a consequence of the very what if questions we had going back to Hollywood and the cultural interpretations. In other words, the question that stemmed string theory was, wouldn't it be nice if we had supersymmetry, if the topology of the universe fit a certain way? And the answer is you could get a universe much like ours, but in order to do that, we have to add all of those other dimensions, call them extraneous terms if you'd like,
right,
to make that work. And this is where we get away from history and more into opinion here, but this feels like a cop-out to me.
well, I see where you're coming from. I don't want to cut you off.
No, go right ahead.
I see where
It's a
you're coming
discussion,
from. But I've talked, my career, I've interviewed many eminent quantum field theory people and cosmologists, and they're like, for example, there was someone who passed away last year that I've interviewed several times, Stanley Deser, who was working on not models with just 3+1 dimensions, with particles, not with strings, for years, and bashing his head against the wall trying to get solutions. And then string theory came out, and it's like, okay, this works because we don't have to worry about infinite terms. We have finite terms, and it predicts certain types of particles. So he said it's obvious that we have to move in that direction. Another, like Bryce DeWitt, the one who came up with the many worlds thing, I interviewed him, and he said string theory is the only game in town because it's the only viable theory, and all the other theories have been discarded, like they don't work.
how long ago was that?
That I interviewed him about 20 years ago. So
Question about string theory. So a few years ago, it seemed to be very, very popular, but it seems to be losing popularity. Is that right?
well, a lot of people are just kind of giving up on unification, and I don't blame them in some ways. I mean, if you assume that Einstein's general theory of relativity is perfect, and you assume that the standard model, which is the theory of electromagnetism and strong and weak nuclear forces, is perfect, it makes life a lot easier, because then you can say, okay, you have one theory for gravity and another theory for the other forces. But then if you want to say all the forces at one point were the same force, there was only one force, and that split up, or that somehow gravity must be related to the other forces, then you run into problems. But if you just say, okay, we give up and we just say that there's two theories of nature, one of them that operates cosmologically on a large scale and the other that operates on a small scale, and there's no connection between the two of them. We're just going to say that there's no connection. Then it makes life easier, but then a lot of people are kind of like, well, why do you have these things called forces and they're so different from each other? Yes.
So I'm dropping back to the stupid. You've thought about this a lot, because written this book. So if you were observing from the outside, what's a multiverse look like? A stack of records, bubble fast, or lots of them disappearing fast because of that cosmological constant? Or
We have,
what's it look like?
if you could step out of it, you would see bubble universes of different sizes.
Bubble.
Yeah. But it's kind of hard to picture. But I have, you know, see, where's the image? Things like this, like that. But it's really hard to picture because it's in a higher dimension.
Could you jump back a few slides? There was a word that caught my eye. Yeah, keep going. And I think it talked about the difficulty because they're far away. There was a, where was it? Oh boy. There we go. Impossible to detect it because enormous distance is involved. Now, maybe I'm thinking too literally and three-dimensionally, but is that like, I'm thinking like California is really far away if I'm walking. Is it like, do you mean like a distance in that sense? I mean, they're not far away in our three-dimensional sense of the universe, right?
Well, if you have two bubbles and let's say you have the whole cosmos is expanding and you have our universe is something that blew up and then another section blew up. They're beyond observability
Thank you very much.
now because they are like, they would be possibly trillions of light years away from each other
Okay.
at this point.
I would think distance in a dimension higher than one of our three.
Well, that's another way of looking at it.
Okay.
But,
So you represent universe being flat. Flat.
well,
Or not.
so if the actual universe is flat, then that means that it's like a box that if you went in any direction, it's like a box-like shape. So that if you go in a straight line, you would just keep going in any direction. But the reason observable universe is like a bubble is because that's the limit of what we can see is like a bubble. Because you can see the same distance in all directions. And so that's the distinction.
Are there any questions online? Want to make sure, and we did mute you, the online folks, so if you have a question, feel free to unmute yourself.
I was reading about like in the far future, like trillions of years from now, like when potentially black holes begin coalescing, like if they start merging, there was something called tunneling, where it could tunnel into different potential new universes or maybe new big bangs. I mean, can you elaborate more on that?
Yeah, there's a theory of that a black hole represents an extreme warping. And under some circumstances, it can create a kind of throat to another part of space. But normally, for a standard black hole, if you tried to enter the throat, it would collapse and not let you through. But there is something called traversable wormholes, which is a way of sort of designing, custom making something like a black hole, but that would have a throat that you could pass through. And Kip Thorne worked on that. And that's the basis of the film Interstellar.
Yeah, guys, I know I'll take a peek at your top 10 list. Is there a single movie that maybe, oh my gosh. I thought Interstellar did a great job of making a great Hollywood movie that tried its hardest to adhere to actual physics. What would be your number one movie that represented a multiverse theory the best from a scientific standpoint? Or is it impossible because of, like you made the comment that such a movie would be so horribly boring?
That's right. So you'd have to have, in the quantum multiverse, you'd have to have like two versions of a scientist saying, oh, that's where the electron is. No, that's where
Right.
the electron is. And then for a cosmological multiverse movie, you'd have to say, well, we think there's another universe out there, but we won't be able to reach it.
Right, yeah. The 2-second movie.
Yeah,
What
so
did you think about the shows like Sliders and Quantum Leap where they explore different universes in every TV show?
they're fun. I mean, I like those kinds of shows the ones where you go to different possible realities. There've been a lot of shows like that, and ones involving also with time travel and changing the course of history. Some physicists don't like science fiction, but I'm a big fan of science fiction. So I read a lot before I became a physicist. Pardon?
Fringe, it was an old television show.
Oh, okay.
Older television show
Yes,
from the early to mid 2000s. So,
yeah.
but
So, yeah, so,
I don't know what that much really.
yeah, I know.
Yeah, they're 1990.
Sorry.
so are there any other questions or we stop here?
Any other questions? Otherwise, let's give it up. Thanks to Prof. Again, a couple of final reminders. He has books. There are refreshments, so please continue to hang out and socialize. We'll see you in December for our swap meet holiday party, and keep your eye on your email in the groups.io for extra communication. So see you guys around.
Everybody do your part, keep the snacks.
It's a
And buy a book.